So in this lesson, we're going to sample with means. And what that means is that we're sampling with the statistical mean or the average. So there's really two things that we'll focus on, either means, which is the average, or proportions, which is when you get a percent of a whole. And so that's what we'll look at next. But what we're trying to do is to be able to answer questions about what we can expect to happen from our sample based on the characteristics of the population. So we know previously when we studied the normal model that we would put n and then mean and then standard deviation. And because we know that as we continue to sample more and more that our distribution becomes normal, we will be using that normal model again. Now, the mean of the sample, so if I asked you for the normal model, the mean of the sample, notice the way we're denoting that, the mean of the means of x's is equal to the mean of the population. So if I know the population mean, I just use that mean. The standard deviation of the sample is not the same as the standard deviation of the population. So if we have the standard deviation of the population, notice we're going to take the standard deviation divided by the square root of n. So that's going to give us our new standard deviation. And again, that standard deviation will be for the sampling distribution. Now, as we move forward through this course, we're going to focus a lot on assumptions and conditions. And of course, this is for means, so the averages. And what this is saying is that we really need all of these conditions to be met in order for us to be able to use the normal model. So this is basically us checking if it checks all the boxes so that we can then use the normal model and perform our calculations. So the first is that it has to be randomized. So notice when he did his bunny experiment, the bunnies that he chose were randomized. The 10% condition we talked about last week, actually. The sample that you have must be less than 10% of the population. And again, that just helps with randomness. The independence assumption, the results of each sample must be independent of one another. So we've talked a lot about independence. And then the large enough sample, again, all of that helps essentially with randomization. So here are our steps. And you will do this a lot, particularly in case study type questions where I make you go through the whole process, as opposed to in my stat lab, where they'll ask you about, each part sort of separately. So for the first thing, we're going to check the conditions. And again, we just talked about randomization, 10%, independence, large enough. And again, this is specifically for means. So when we do proportions, it's going to be similar, but just a tiny bit different. And then we're going to perform the needed calculations. So we're checking the conditions. And part of this, which I didn't put on this list and should have, is that then I should say, because the conditions are met, I can use the normal model, and then you can list that mean and standard deviation here, or you can find those as you do the calculations. So the calculations that we're going to be dealing with, because it's a normal model, we're going to use a z-score. So we should be familiar with this because we did some practice in Mod 2. So recall that z-scores are observed minus expected over the standard deviation. Now, the only thing different here is that, remember, our standard deviation is the standard deviation of the population divided by the square root of n. So it's still observed, which is our mean, that's the y bar, minus the mean of the population divided by the standard deviation of the sample. So it's good to draw a picture of the bell curve to help you to determine, are we finding the area to the left or to the right of our value? And then we're going to state our conclusion. So let's take a look at what this looks like all together. So at birth, babies average 7.8 pounds. So the first thing you look at is the fact that it says average, and we know that average means a mean. So that's how I know that I'm going to be doing this process instead of the one with proportions. So the standard deviation is 2.1 pounds. So I've got 7.8 pounds for the mean and 2.1 for the standard deviation. A random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. This is our observed value. This is expected, and then standard deviation, we'll have to do some calculations. The question is that unusually low? So first thing we need to do is understand the question. if we've got our curve here, that was a bad curve, but 7.8 is what we expect, and we've got 7.2, which is obviously to the left, and if it's unusually low, that would mean that the weight is 7.2 or less. So this is the area that I'm finding, and it's good to know that coming into it so you can do your calculations correctly. So the conditions, first random, there are 34 babies were randomly selected. 10%, obviously 34 is less than 10% of all babies born. Independence, the birth weight of one baby is independent of another baby's weight, unless of course they're twins or something, but we're going to assume that randomly selected babies won't be twins. And then the one that we didn't really talk about much is the large enough condition. So when dealing with means, N has to be at least 30 so that we can assume that the sample is large enough. So because these conditions are met, we can use a normal model, and our normal model is the 7.8, which is of course our average from the question. And then this, remember, we're taking the standard deviation that's given to us and dividing by the square root of n, and n is of course the number of babies that we're sampling. So this is our normal model. One thing I want to caution you with here, don't round this off too much if you're going to use this in a calculation. And then we would draw a picture. This is the same as the picture that I drew up here. And then we're going to perform the calculations. So 7.2 minus 7.8. Now, a lot of times I just want to point out that people will do this calculation here. So they will, instead of writing 0.36, they'll write the 2.1 divided by the square root of 36 down there so that their answer is more exact. And notice I get a z-score of negative 1.67. So the z-score of negative 1.67, and now I'm going to find the probability. So the probability that the mean is less than 7.2 is equal to the probability that z is less than negative 1.67. So this is the mean is less than, and notice I used less than because I'd shaded to the left. Then z is less than, and then essentially I'm using the calculator or StatCrunch to show this work. So notice here, if I'm using the calculator, then I'm going to do norm CDF negative 10,000, which is the left-hand side of my curve, comma negative 1.67, which is the right-hand side. So remember, this is essentially negative infinity, but we can't put negative infinity in there. And then the negative 1.67, mean is 0, standard deviation is 1, and that's where I get this value. You can use your calculator. You can also use StatCrunch for this. Again, if I'm using StatCrunch, I'm going to go to Stat and Calculators and Normal, and that brings up my little picture. Remember that I am going to use my mean of 0, my standard deviation of 1. I want less than negative 1.67, and then I'm going to compute, and notice that gives me the same result. Again, you can check this to make sure that you did your z-score correctly by using the mean of 7.8 and the standard deviation of 0.36, and then that would be less than 7.2, and I should get that same solution again. But remember, if you're doing this for a case study, I'm going to want to see all of this work. If you're doing this for a MyStatLab question, you can just go straight to this step to actually just compute it without, doing too much work. So again, then we would state our conclusion in context, which is that according to the normal model, only about 4.75% of samples of 34 babies are expected to have mean birth weights below 7.2 pounds, so the samples of babies near the factory appear to have an unusually low mean birth weight. The other way that we might use sampling with means is with the empirical rule, and we should be familiar with the empirical rule. We've learned it before. Again, with the normal model, we expect about 68% of our samples to fall within 1 standard deviation, about 95 within 2 standard deviations, and 99.7 within 3 standard deviations. So that should all sort of be familiar to us. Please keep in mind that the empirical rule is really just an estimate. It's not the exact value. So if they're looking for an exact value, you should always use the z-score and the probability. But if they ask us, like they do here, describe what we might see in a random sample of 50 cars when we're looking at speeds of cars on the highway with a mean of 52 and a standard deviation of 6, we're going to use the empirical rule because we're going to describe in general what will we expect to see. So first thing we'll do, of course, is check the conditions. We know that it's random because they told us a random sample of 50 cars. And notice when I'm checking the conditions, I'm not just saying random, yes, 10%, yes. I'm actually talking about each one, which is what you should do on a case study. 10%, 50 is obviously less than 10% of cars on the highway. Independence, car speeds in general are independent, especially because we're choosing them randomly. So we're assuming we're not going to have two people next to each other drag racing. And then large enough, n is greater than 30, so we can assume the sample is large enough. The calculations that we'll perform is, of course, that our mean is 52, which is what we would expect from the actual population. The standard deviation, we're not going to use 6. We're going to use 6 divided by the square root of n, which is 50, so 0.85. Because the conditions are met, we'll use a normal model, and the normal model is n 52, 0.85. So the mean of 52, 0.85 is our standard deviation. To write then our empirical rule, we would then just start with 52 in the middle. We would subtract 0.85 as we go to the left, so minus 0.85, minus 0.85, minus 0.85. We would add 0.85 going to the right, so notice I've added, added, added. And of course, we've got our 68, 95, 99.7. Now, if I state my conclusion, I would then just essentially write out what I see in the model. We expect 68% of the samples of 50 cars to fall between these two values, 95 between these two values, and 99.7 between these two values.